The electromagnetic spectrum includes many different forms of electromagnetic radiation. The electromagnetic spectrum includes things like gamma rays, X-rays, microwaves, visible light, but really everything on the electromagnetic spectrum is called light. So even microwaves, radio waves, those are light, and they all behave the same way. They all exhibit wave-like behavior as it travels through space. So this is the electromagnetic spectrum. You can see here the wavelength is labeled at the top, the frequency is at the bottom. As wavelength goes down, frequency goes up. They are inversely related. And there is a small portion of the electromagnetic spectrum that is visible light. That is the only part that we can detect with our eyes. But if we could see the entire thing would be colors, would be light. We just can't detect it. So light has a dual nature. Light has characteristics of both waves and particles at the same time. Those particles are called photons. This is a video. We're not going to watch it. This is cool because this is the first picture that was ever taken of the dual nature of light behaving as a wave and a particle at the same time. So the top part is light as a wave, that's why it's wavy. The bottom part is light as a particle. The size of the waves indicates the energy. So red light is the lowest energy, that's why it's the smallest little waves there, and then purple light is the highest energy, that's why it's the biggest waves. And this video is just how they took that picture. Characteristics of waves. Waves have a wavelength. Symbol for wavelength is lambda. That is the shortest distance between equivalent points on a wave. So it could be the top of one to the top of another. Could be the bottom of one to the bottom of another. Those are both the wavelength and they are the same distance. Because it is a length, the SI unit for wavelength is the same as the SI unit for length, which is the meter. Frequency symbol is like a V kind of thing, is the number of waves that pass a given point per second. And as you can see, the shorter the wavelength, the higher the frequency. The SI unit for frequency is hertz, which is the same thing as inverse seconds. So it's the same thing as 1 over s, or s to the negative 1. The final characteristics of waves is speed. So all electromagnetic waves, including light, visible light, travel at the same speed. They all travel at 3 times 10 to the 8th meters per second. The symbol for this is a lowercase c, and it is a constant. All waves travel at 3 times 10 to the 8th meters per second. So using the fact that that is constant and using the fact that we know that wavelength and frequency are inverse, we can derive this formula that says that the speed of a wave, which again is constant, is going to be equal to the wavelength times the frequency. Let's do a couple problems there. So what wavelength of light has a frequency of 4.61 times 10 to the 14 hertz? So we're using c equals wavelength times frequency. Again, c is a constant, 3 times 10 to the 8th meters per second. Wavelength is my unknown. Frequency, 4.61 times 10 to the 14. I'm going to write it as inverse seconds just so you can see units canceling here. We'll rearrange our equation to solve for wavelength. So wavelength is c over v. And then just go ahead and plug in. So wavelength is 3 times 10 to the 8th meters per second over 4.61 times 10 to the 14 inverse seconds. So the seconds end up canceling, which makes sense because you want the unit of wavelength to be meters. When I solve this for wavelength, I get 6.51 times 10 to the negative 7 meters. It's pretty much the same thing if I have wavelength and I'm solving for frequency. So c equals wavelength times frequency. C constant, 3 times 10 to the 8th meters per second. Wavelength is 5.6 times 10 to the negative 9th meters. Frequency is my unknown. Rearrange to solve for frequency. We get frequency is c over wavelength. that's going to be 3 times 10 to the 8th meters per second over 5.6 times 10 to the negative 9 meters. Meters will cancel. And so you are left with 5.36 times 10 to the 16 hertz, or actually, I'll write it this way, inverse seconds, because that's what you end up with up here, which is the same thing as hertz. The wave model of light cannot explain all the ways that light interacts with matter. For example, how metal glows when it is heated. Iron is gray at room temperature, and as it gets heated, it starts to glow red, then it glows orange, and then it glows blue. And if light always behaved as a wave, it would go through the entire rainbow. So it would go red, orange, yellow, green, blue. So it doesn't. It goes right from red to blue, which is kind of strange. Another thing that cannot be explained by the wave nature of light is the photoelectric effect. In the photoelectric effect, electrons are emitted from a metal surface only when a light at or above a certain frequency shines on that surface. So the certain frequency, you can think of that as the color. So electrons are only emitted when a certain color shines on the surface of that piece of metal. I could shine a super bright red beam of light at that metal for hours, nothing's going to happen. As soon as I shine the faintest beam of blue light on that metal, boom, electrons are ejected. So if light was always just a wave, then the energy would build up, right? I could shine the red light and the energy would build up and eventually it would start ejecting electrons. But that's not what happens. Einstein proposed the dual nature of light to explain the photoelectric effect. So he says that you can think of light as a beam of little bundles of energy called photons. And we know from that picture that shows that light is a wave and a particle at the same time that this is true. So a photon is a massless particle that carries a quantum of energy. So what is a quantum? The quantum concept states that matter can only gain or lose energy in small specific amounts called quanta. So energy and everything actually is not infinitely divisible. There's a smallest division that you can get. So if energy was not quantized, it would be like a ramp. And so this little particle could just continuously gain energy and go up that ramp. And so if that particle was an iron atom, as it gets heated, then it would go through all of the colors of the rainbow. But energy is quantized, which is like a set of stairs. So here's my iron atom, and it jumps up to the red step. And then from there, as it absorbs more energy, it'll jump up to the orange step. And then finally, it will jump up to the blue step. And a quantum is the size of that step. So a quantum is like here to here. That's one quantum. And yes, quanta is plural. Quanta can be different amounts. The steps are different sizes. But a quantum is the minimum amount of energy that can be gained or lost by an atom. We can actually calculate the energy of a photon using this equation, Planck's constant times frequency. So a photon carries one quantum of energy. And we can calculate how much energy that is by doing Planck's constant times frequency. Planck's constant is a constant, 6.626 times 10 to the negative 34. The unit of that is joules times seconds. So every object gets its color by reflecting a certain portion of visible light. That color is determined by the energy of the reflected photons. So if I have violet light that really just wants to skip that one, that has a frequency of 7.230 times 10 to the 14 hertz, and I want to calculate the energy, I can just use my energy formula, E equals HV. Energy is unknown. H is Planck's constant, so 6.626 times 10 to the negative 34 joules times seconds. And then my frequency here is 7.230 times 10 to the 14 hertz, which again is inverse seconds, 1 over seconds. So when I plug that in, 4 joules times seconds times 7.230 times 10 to the 14, 1 over seconds. You can see how seconds will cancel. And I'd be left with an energy unit, joules, so that makes sense. You get 4.790 times 10 to the negative 19 joules. In this question, we have an amount of energy, and we are asked to calculate the wavelength. So I have my two formulas. Energy is Planck's constant times frequency, and the speed of light is wavelength times frequency. Since they both have frequency in them, we can just do simple substitution to solve this problem. So I'm first going to rearrange my energy equation to solve for frequency. So frequency is energy over Planck's constant. So that's 7.21 times 10 to the negative 19 joules over Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. So joules will cancel. I will be left with a frequency of 1.09 times 10 to the 15 inverse seconds. I can then plug that in. Let's solve this one for wavelength. Wavelength is c over frequency. So just plug that number in for frequency there. So wavelength is going to be 3 times 10 to the 8th meters per second over 1.09 times 10 to the 15 inverse second. So seconds again ends up canceling. I'm left with the unit of meters, which makes sense because it's a wavelength. So 2.75 times 10 to the negative 7 meters is the answer to that one.